In the vast silence of space, moments of true anticipation are rare. They rise slowly, like distant stars emerging from behind cosmic dust, until suddenly they command the world's attention. Today, humanity stands before one of those moments, a moment shaped not by fear, but by curiosity, not by spectacle, but by discovery. For weeks, scientists, observatories, and space agencies across the globe have been watching a mysterious traveler, 3I Atlas, an interstellar visitor slicing through the inner solar system with quiet precision. Its path, its structure, and its behavior have raised questions that challenge the boundaries of cometary science. And now, after more than 40 days of delay, NASA is expected to release the long-awaited high-resolution images captured by the HiRISE camera aboard the Mars Reconnaissance Orbiter, a camera powerful enough to rewrite what we think we know about objects wandering between the stars. But before these images become public, let us trace the scientific story that brought us here. A story of physics and geometry, of interstellar debris and cosmic forces, of worldwide anticipation, and the timeless human instinct to wonder. Interstellar objects are extraordinarily rare. In the recorded history of astronomy, we have confirmed only two such visitors, Oumuamua in 2017 and Borisov in 2019. Both transformed our understanding of what kinds of objects drift between the stars. But 3IA Atlas is different. Detected in mid-2024, it entered the solar system on a trajectory that betrayed its foreign origin, a path not bound to the sun, but merely passing by it, like a traveler moving between distant worlds. Early images suggested a diffuse coma and a surprisingly bright profile. Then came the anomaly, an anti-tail seemingly pointing toward the sun rather than away from it. To astronomers, this was not merely unusual, it was extraordinary. A comet's dust tail is shaped by the gentle but relentless pressure of sunlight pushing dust outward. An anti-tail, however, hints at geometry more intricate than simple radiation pressure. Perhaps the perspective from Earth, perhaps an unusual distribution of heavy dust, or perhaps a more complex physical process still unfolding. But Earth, at that moment, could only see Atlas from an angle that distorted the truth. Hubble's observations were valuable, but limited. We needed another vantage point, a clearer perspective, a side angle unobstructed by solar glare. That perspective existed only on one world. Orbiting Mars, the HiRISE camera stands as one of humanity's most advanced eyes in space. It was designed to map Martian cliffs, dunes, and craters with breathtaking detail. But occasionally, it turns that precision outward, toward passing comets, asteroids, and the mysteries drifting beyond Mars' orbit. On October 23rd, HiRISE captured its best opportunity yet. At 29 million kilometers away, Atlas passed within range. The camera recorded the object at the edge of Mars's orbital neighborhood, gathering data with clarity far beyond what Earth-based telescopes could offer. From Mars, the geometry was perfect, a side-on view, free from the overwhelming brightness of the sun. HiRISE could not resolve the nucleus itself. It was still too small, too distant. But in science, resolution is not everything. A single bright pixel can reveal nucleus size. The spread of brightness reveals dust density. The angle of jets reveals rotation. The shape of the tail reveals dynamics of mass loss. In astronomy, clarity is not just seen, it is interpreted. When news broke that NASA had imaged the object, the world expected immediate release. But nothing came. For 43 days, no public images were posted. Speculations spread across social media, news reports, and scientific discussions. Why the silence?
Some imagined secrecy, some imagined fear, some imagined cover-ups. But the truth was far simpler and far less dramatic. During that period, the U.S. government operated under a continuing resolution freeze, which slowed or halted various administrative pipelines, including those involved in public release of spacecraft data. HiRISE's images were simply caught in bureaucratic traffic. The universe had kept moving. Atlas had kept moving. Only the paperwork stopped. Meanwhile, other nations filled the silence. European telescopes released their analyses. China's Tianwen-1 shared images from Mars orbit. Japan produced color curves and spectral estimates. Amateur astronomers compiled daily tracking logs. And so, in this global symphony of data, the missing piece, the one held back by delay, was NASA's high-resolution view. A view that may hold the clearest answers.
Of all the features observed so far, none has generated more debate than the anti-tail. Why would dust appear to stream toward the sun? Several explanations exist. Earth's viewing angle might have created the illusion. Larger, heavier dust grains might fall back toward the orbital plane. Sublimation jets might be releasing material along unusual trajectories. The objects might be fragmenting, creating a complex dust environment. But one possibility, rare, speculative, and scientifically fascinating, lingers at the edge of the discussion. The idea that the jets may behave in a structured, directional manner rather than chaotic, natural venting. HiRISE's vantage point from Mars allows us to test these scenarios. If the anti-tail disappears in the new images, the anomaly was likely geometric. If it persists, with curvature, structure, or extension, then the physics is more complex than expected. Science does not leap to extraordinary conclusions. Science eliminates possibilities one by one until the truth remains.
Another major puzzle is fragmentation. Early brightness patterns implied enormous mass loss, possibly billions of tons. Such a rate might require a much larger nucleus than expected, unless Atlas has fractured into multiple pieces. Fragmentation would explain the high surface area implied by dust output, the irregular jets observed near perihelion, the variability in brightness over time, the unusual dust structures surrounding the object. HiRISE may reveal small subnuclei drifting in the coma, uneven brightness regions, separated fragments following the same orbital arc, complex plumes suggesting breakup. If confirmed, Atlas would not be a single body, but the ruins of one. If not found, then the nucleus may be intact, and its behavior more unusual.
To understand Atlas, we must compare it to known giants, such as comet Bernardinelli Bernstein, the 100-kilometer-wide Oort cloud behemoth discovered in 2014. BB behaves exactly as the models predict: slow, heavy, predictable sublimation even at enormous distances. Atlas does not fit so neatly. Where BB confirms the rules, Atlas presses against their edges. Science thrives in the gap between what is expected and what is observed. When NASA finally releases the HiRISE images, scientists will examine them pixel by pixel. They will ask, how large is the nucleus, truly? Has fragmentation occurred? Is the anti-tail real or an illusion? Are the jets chaotic or structured? Is the dust symmetric or directional? How does the brightness profile compare to comet models? A single afternoon with the data may answer questions that months of speculation could not. And whatever the results,
The process will be open, public, and collaborative. Science does not advance through secrecy. It advances through shared evidence. In the end, Atlas is not a threat. It is a rare chance to observe something ancient, something foreign, something shaped by forces beyond the sun's domain. It reminds us why humanity explores, why we build telescopes, why we send orbiters to distant worlds, why we study the sky generation after generation. Because curiosity is our oldest form of propulsion. Long before we built rockets, we looked upward. Long before we reached Mars, we imagined what might pass beside it. Long before we understood the stars, we wondered what secrets drifted between them. Now, one of those secrets has arrived at our doorstep. And soon, a camera orbiting a planet we have not yet set foot on will show us the clearest view ever captured of an object born in another star system. When that moment comes, the world will pause, not in fear, but in fascination. Because every pixel, every shadow, every faint jet, every glimmer of dust carries a story billions of years old. And we, as a species, are finally ready to listen. Stay curious.